Hello APC Mechanics students, today we'll solve the past paper FRQ 1999, exercise 3. Then as shown above, remember that always the figure appears above the text itself. As shown above, a uniform disk. A uniform, it means that the center of the disk is located geometrically at the center, is mounted to an axle and is free to rotate without friction. A thin uniform rod is rigidly attached to the disk so that it will rotate with the disk. A block is attached to the end of the rod. Properties of the disk, rod, and the block are as follows, which means that the system, which is a composite consisting of the disk, the rod, and the block, they rotate together. Now we have the information for the disk, the rod, and the block. The system is held in equilibrium, which means we can apply the condition of equilibrium with the rod at an angle theta 0 to the vertical as shown above, by a horizontal string of negligible mass with one end attached to the disk and the other to a wall. Express your answers to the following in terms of m, r, theta 0, and g. Then now in this exercise, whenever we determine an answer, we need to make sure that it's being expressed in terms of these. Then we need to determine the tension in the string, and this is done using Newton's or using a condition of equilibrium. Now, what are the forces that are acting on the system, and which system we will consider? We will consider the disk, the rod, and the block. So what are the forces acting on our system? We have the tension along the string, so let me say this is F tension, and we have the pull of gravity on the rod, or let me say we have the mass of the disk, which basically the pull of gravity. That would be Fg of the disk, and we have the reaction at the axle. Now, in addition to these two forces, we have the pull of gravity of the rod acting at the center of the mass if we're assuming that the rod is of uniform mass distribution, so that's the center. Then Fg of r. And there is also the pull of gravity acting on the block vertically downward. Then the rotation will occur around this axis. Now joining this point with these points, then that would give us the radial direction, and these are the tangential directions for each force. Now because this is the vertical and the angle theta 0 is given with the vertical, and these are vertical forces, then that would be theta 0 as well, and that would be theta 0 as well. Then these angles are given by pi by 2 minus theta 0. Then we need to apply the condition of equilibrium, and let me say that the torque nut is equal to 0, and that is because we are at equilibrium. What are the forces? We have the torque produced by the tension plus the torque of the pull of gravity of the disk, let me say tau d, plus tau of the axle, plus the tau due to the rod, and the torque produced by the block, that would be equal to 0. Now we can directly eliminate this and this one, simply because the pull of gravity of the disk and the axle, they passes through the axle of rotation, which is this one. Then we're left with these three. Let me assume the positive direction to be anti-clockwise. Then the torque produced by these two pull of gravities is positive, and the torque produced by the tension is negative. Now let me start by determining the torque produced by this pull of gravity, which is Fgr. Now here, if you notice carefully, the mass of the block is 2m. So let me write here that this has a mass 2m, and the rod has a mass given by m. Then the torque produced by the rod is given by its mass, which is m. Or let me start by the torque produced by the tension. The torque produced by the tension is in the negative direction. The tension is being applied tangentially, then it would be the radius of the disk, which is r. so the radius of the disk is r, multiplied by the force of tension, so that would be minus Ft multiplied by r, plus the torque produced by the rod, which is the force itself given by m multiplied by g. Now the distance from the point of application of the force to the center is given by r because the length of the rod is given by 2r, multiplied by cosine of the angle between the force and the tangential direction. If this is theta 0, then that would be pi by 2 minus theta 0, and cosine of pi by 2 minus theta 0, that would be sine theta 0. Now plus the torque produced by the pull of gravity acting on the block. The mass of the block is 2m, then that would be 2m g multiplied by the distance from here to the center, which is the double of r. Then let me say 2 mg, the double of r, and similarly that would be sine theta 0. Let me show you. Because this is the angle theta 0, now we need to multiply by cosine of this angle, which is pi by 2 minus theta 0, which is the angle between the force and the tangential direction, which give us sine theta 0. And we're interested in determining the tension. Now this is minus. If we drag these to the other side, they would be minus. The minus cancel everywhere, so the tension provided by the string is given by mgr sine theta 0 plus 4 mgr sine theta 0, and finally the tension would be equal to 5. Sorry, here for the tension I forgot something. It should be the tension multiplied by r, which is the radius of the disk. So here we have r, then r with r cancel. This added to this would give us 5 mg sine theta 0. And indeed our answer is being expressed in terms of mg and theta 0. They won't tell you that express your answer in terms of sine because sine is a function. Now moving on to the next question, they're telling us the string is now cut and the disk rod, the block system, is free to rotate. The moment the string is cut, then we have lost tension. Determine the following for the instant immediately after the string is cut. So we are talking as if we have stopped time. We've cut the string and the angle is still given by theta 0. We need to determine the magnitude of the angular acceleration of the disk, and the only way to do that is by applying Newton's second law for rotation. So let me say apply Newton's second law, and remember, whenever we're doing a big law, we need to mention the law that we're using. It's important to mention apply Newton's second law. Now whether for rotation or translation, it's not much a difference. And Newton's second law is given by tau naught is equal to I multiplied by alpha. And now what are the net torques acting on the system? We have lost the tension, so the only two torques acting on the system are given by this one and this one that we have determined previously. So let me write. Then we can directly write mgr sine theta 0 plus 4 mgr sine theta 0. And what does I represent? I is the rotational inertia of the system around our axis of rotation. And here, if you notice carefully, our system consists of 3 massive bodies given by the disk, the rod, and the block. So we need to include the moment of inertia for these 3. Then we have I for the block plus I for the disk plus I of the rod multiplied by alpha, and we're interested in determining the value of alpha. That would be 5 mgr sine theta 0. Now what is the moment of inertia of the block around the axis? Now notice that the block is treated as a particle, and we're interested in determining the moment of inertia of this particle around this axis of rotation. And recall that the moment of inertia of a particle about a certain point is given by the mass multiplied by r squared. The mass is given by the double of m, and the distance is given by the double of r. That would be to the power of 2, which is basically 8m r squared, but let me write it explicitly as 2m multiplied by 2r to the power of 2 plus the rotational inertia of the rod around the given point. And indeed they're telling us the moment of inertia of the rod about one end, which is given by 4/3 mr square. Sorry, that would be for the disk. And for the disk is given by 3/2 mr square. Now that would be 5 mgr sine theta 0. Now before I continue, because we're interested in determining alpha, so what would be the expression of alpha, because it's a free fall under gravity? It should have the following form: alpha, which is given by g divided by r, because this is the only way that we can construct to give us meter or radians per second square. And here in the coefficient, this depends on the engineering of the problem. Now here we would have 8 mr square plus 3/2 mr square plus 4/3 mr square multiplied by alpha. And if we add the following fractions given by 8, 3/2 plus 5/3, we would have 65/6. Then that would be 5 mgr sine theta 0 given by 65/6 mr square multiplied by alpha. We can start applying the cancellation effect, and we can simplify 5 with 65, that would be 13. Then at the end we would have g sine theta 0 is given by 13/6 r multiplied by alpha. We're interested in determining alpha. Then alpha in this case is given by a coefficient which is 6/13 sine theta 0 multiplied by g, and indeed our anticipation is correct, and we don't forget that we should divide by r. So this is very important. Whenever you know that your structure is gonna be something that you already know because you understand physics, that would save you if you have done any mistake, as I have done so. Now in idea number 2, we need to determine the magnitude of the linear acceleration of the mass at the end of the rod, and we know that so here this title corresponds, idea 1 and idea 2, they correspond for, still we're talking at the instant immediately after the string is cut, so we have fixed time and fixed angle. And we know that in this case the linear acceleration is related to alpha via a radius. So a is given by alpha, but which radius? We're talking about the linear acceleration of the mass at the end of the rod. And this mass, or the block at the end of the rod, is being away a distance of double of r from the center, so we will use this radius, which is the double of r. Then alpha, which is given by 16/3 sine theta 0, g divided by r multiplied by r with r cancel, and sorry, here we have the double of r, so r with r cancel, 2 with 6 is 12. Then the linear acceleration at the end of the rod is given by 12/13 given by multiplied by sine theta 0 multiplied by g. Now part C, which is the last part in this exercise, as the disk rotates, the rod passes through the horizontal position shown above. We need to determine the linear speed of the mass at the end of the rod for the instant the rod is in the horizontal position. So basically what's happening here is that when the string is cut, so the rod will rotate to occupy the horizontal position. We're interested in determining the linear speed of this rod. One way to think about it, since we have the acceleration, we can determine the linear speed, and this is a bit challenging. Why? So first of all, you cannot use kinematics in any sense, simply because this, although it's constant, but we have determined its value immediately after the string is cut. So if you wait until time evolves, the value of theta 0 will change, and it's not constant, because as the rods start making or start falling down, the value of theta with the vertical will change, which means that theta is a variable, which means again that the acceleration is a variable. So you cannot use kinematics. One way to do it is using calculus, but you need to apply a change of variable, which is a bit challenging. So always whenever we have a free rotating rod under the influence of gravity, the first thing that you should think of is the conservation of energy, because energy is about initial and final state. But before doing so, we need to specify our PE level that will allow us to eliminate the final gravitational potential energy. For that, let me say take the PE level to be the horizontal passing through the rod in the final position. And now we're gonna say apply conservation of energy. So in this case, we have energy initial is equal to energy final. Then kinetic energy initial plus gravitational energy initial is equal to kinetic energy final plus gravitational potential energy final. That would be 0 based on our choice, and the system is released from rest. Now gravitational potential energy initial. So here we have three masses given by the disk, the rod, and the block. Because the disk is perfectly rotating, and the center of mass is located at the center. For this reason, we're not going to consider the gravitational potential energy of the disk we have for the rod and for the block. Now that's our PE level. And that's the initial center of mass of the block. So let me say that would be H1. The distance from the center of mass of the block to the PE level, and let me say H2 would be the vertical height of the center of mass, sorry, that's for the block, that's for the rod, to the PE level. Now the block has a mass 2m and its height is given by H1, so let me say the gravitational potential energy of the block is given by mass times g times h, which is 2m gh1, and for the rod it's given by mgh2, and that would be equal to the final kinetic energy here. Because we're talking about pure translation, then it would be half I omega square, and I would be the rotational inertia of the system, and that has been determined in this part, which is given by 65/6 mr square. Now the challenging part is to determine H1 and H2 in terms of the constants that we are interested in, given by mr, theta 0 and g. And also, if you note carefully, this has been indeed expressed in terms of g and r and theta 0, and this has been expressed in terms of g and theta 0 as required from us here. Now H1 and H2, they can be determined from the geometry of the figure. Now let's consider the triangle. Now this point, let me say it's A, this point it's B, and this point it's C. In most of the cases, the height is related by the sine of the angle, but it's not always true. You need to be very careful. Now we're interested in determining H1, which is the side AB of this triangle. Let me draw it here. So that's the triangle. This is A, this is B, that's H1, that's C. This is 2r, and that's the angle theta 0. Now H1 is related to theta 0 via a cosine, not a sine, because this side is an adjacent for the angle. Then cosine theta 0 would be H1 over 2r, then H1 would be 2r multiplied by cosine theta 0. Now similarly for H2, if you consider this triangle here, H2 would be again cosine theta 0 multiplied by the adjacent and multiplied by the hypotenuse, but the hypotenuse in this case is r, so that would be r cosine theta 0. Then the heights, so that would be 2mg 2r multiplied by cosine theta 0 plus mg r cosine theta 0 is equal to half 65 divided by 6 mr square multiplied by omega square. That would be 5 mg r cosine theta 0. That would be equal to 65 over 12 mr square omega square. Now m with m cancel, r with power 2 cancels, 5 with 65, that would give us 13, and we're interested in determining omega square. Then omega square is given by, now 12 is done, we're gonna take it up, so 12g cosine theta 0 divided by 13r. But remember that we're interested in the linear speed of the mass at the end of the rod and not omega, and we know that in this case omega is equal to v divided by the radius, and the radius that we're talking about is the double of r because we're talking about the end of the rod. So that would be v square divided by 4r square, because the double of r to the power of 2, that would be 4r square, which is equal to 12g cosine theta 0 divided by 13r. Here, because the speed is due to a free fall, we would consider that v is given by the square root of a coefficient multiplied by gr. This is the only way that we can construct speed. Now this with that would cancel. 4 multiplied by 12 would give us 48, and we have r. Then v square would be given by 48 rg cosine theta. So all of these should be cosine theta 0 divided by 13. Then speed indeed is given by a coefficient given by 48 cosine theta 0 divided by 13 multiplied by rg. And that's it for me in this video, guys. See you soon in a new one.